Why is FEA needed for nonlinear buckling analysis? Imagine trying to predict how a tall, slender tower will behave when it faces strong winds or heavy loads. It's not as simple as just pushing it and seeing when it falls. That's where understanding buckling becomes essential. Buckling is a sudden failure where a structure deforms dramatically under compression, often leading to collapse. To prevent this, engineers need precise tools to see how structures respond as they approach their limits. Linear buckling analysis is like guessing the breaking point by assuming everything is perfect. It assumes the structure has no imperfections, loads are applied evenly, and deformations are tiny. But in real life, no structure is perfect. Small imperfections in shape, material inconsistencies, or uneven loadings can cause a structure to buckle at much lower loads than predicted. That's why relying only on linear analysis can be risky. It might give a false sense of security, leading to designs that are either too conservative or dangerously optimistic. Nonlinear buckling analysis uses finite element analysis, which is a computer-based method that divides the structure into tiny pieces called elements. This method can simulate how each part reacts as loads increase, capturing the real behavior of the structure. It considers geometric nonlinearities, meaning it accounts for large deformations that change the shape and stiffness of the structure as it buckles. It also includes material nonlinearities, like plastic deformation, which can happen before or during buckling. Another key aspect is the ability to include imperfections naturally. Instead of assuming a perfect shape, the analysis can incorporate actual imperfections, making the results more realistic. This helps predict how real structures will behave under load. Plus, nonlinear analysis can show what happens after buckling begins, revealing if the structure can carry some load or if it will fail completely. This kind of analysis is especially important for slender columns, thin plates, shells, and other structures that bend or deform significantly under load. It helps engineers design safer, more reliable structures by accurately estimating the actual load capacity and deformation patterns. Industries like aerospace, automotive, civil engineering, and mechanical systems relying on this to avoid sudden failures that could be catastrophic. In short, finite element analysis is needed for nonlinear buckling because it captures the true response of structures with imperfections and large deformations. It reveals how real-world structures behave under stress, helping engineers design against failure more effectively. This approach makes products safer, more efficient, and less likely to break unexpectedly.